Okay. Uh, First, I'd like to start with some reflections on Shor's algorithm. Why is Shor's algorithm so important? Uh, it was discovered by Peter Shor in 1995, and it was the main reason behind why uh, people started to working on quantum computation and developing quantum computational algorithms, because Shor's algorithm has deep implications in secure communications, in encryption algorithms. Basically, what Shor's algorithm says is, given a positive integer capital N equals P times Q, P and Q are the two uh, prime factors of the capital N. Shor's algorithm is able to compute P and Q in polynomial time, in the order log square n time, where n is the positive integer that we want to factorize. Shor's algorithm can efficiently decrypt RSA, because RSA depends on prime factorization of large integers, long integers, and also the Diffie-Hellman encryption, which is based on discrete logarithms. So Shor's algorithm is capable of solving these two problems efficiently in polynomial time, which this RSA and Diffie-Hellman, they constitute the basis of most modern encryption schemes. If you look at the best known classical algorithm, which is referred to as the number field sieve algorithm, it has exponential complexity. It is order 2 to the n over 1 over 3. So since capital N is in the exponent of 2, that's an exponential, that indicates an exponential complexity. So this is the best known classical algorithm. As we mentioned, the factorization problem, it's going to turn out to be a period finding problem of a sequence of numbers. In other words, Shor's algorithm will turn out to be the same as quantum phase estimation. It's quantum phase estimation in disguise. The discrete log problem, that's the basis of the Diffie-Hellman encryption, is defined as follows. If you are given a prime P and integers G and A, the problem is to find X such that G to the X equals A modulo P. This is called the discrete log problem, and that's the basis of the Diffie-Hellman encryption. And this is also classically exponentially complex. This is a hard problem classically as well. And as we said, Shor's algorithm is also able to tackle, with the discrete log problem efficiently. In addition, Shor's algorithm can be used to decrypt elliptic curve crypto systems. This is another kind of technique that people use. One of the most common techniques that people use in classical encryption and decryption systems. Additionally, Shor's algorithm can be modified to find hidden structures in abelian groups. Abelian groups are commutative groups. This is another application of the Shor's algorithm. And if we look at it, most of the current crypto systems use these primitives. So as far as we know, Shor's algorithm is not applicable to hidden structures in non-abelian groups. The importance of this is that if this were the case, we could solve the graph isomorphism and lattice-based cryptography problems as well. Lattice-based cryptography is currently the most prominent post-quantum cryptographic algorithm. But although people have worked for, I think, quite a few years now to apply Shor's algorithm on non-abelian, to find hidden structures in non-abelian groups, and also as a consequence of this, to use Shor's algorithm in lattice-based cryptography. Up till now, this research has been inconclusive. So the general opinion is that Shor's algorithm is not applicable to lattice-based cryptography, and as such, this kind of cryptography is the most prominent post-quantum cryptographic algorithm. That is, when we say post-quantum cryptography, we mean cryptography that is resistant, as far as we know, resistant to quantum computation. Another application of Shor's algorithm is homomorphic encryption. Homomorphic encryption means, let's suppose you have a cloud-based computational system. Homomorphic encryption enables computation, running computations on such a cloud-based system without actually encrypting or decrypting the data. So this is, if can be realized, this is a very important application, because that will enable people concerned about security, of their data to run their algorithms or their work on such cloud-based systems without compromising the privacy of the work. So this is another application of Shor's algorithm. As we mentioned, Peter Shor invented this algorithm around 1995 when he was at IBM. Now he's at MIT, a professor at MIT. The problem is, can be stated as given a capital N, a large integer number, we'd like to compute the prime factors P and Q. This problem is believed to be in NP class. In other words, it is exponentially complex classically. I'm saying believed to be, but because in the computation theory, this is not proven. I mean, if someone comes up with a new classical algorithm that solves this problem more efficiently, we don't have proof for that. We don't have the non-existence, proof for that. So that's why I'm saying believed to be in NP class, exponentially class problems. But quantum mechanically, we know that this is in the BQP class, bounded error quantum polynomial class. So this problem can be solved within polynomial complexity in quantum mechanics, as we are going to see shortly. So there is, in other words, there is an exponential speed up with respect to the best known classical algorithm. So this was the first major motivation behind the development of quantum computers. All the other algorithms, quantum circuits that we discussed prior to this, Bernstein-Vezirani algorithm and other circuits, the primitive circuits that early algorithms that we discussed during the past few lectures, they show some speed up with respect to classical computation, but they don't necessarily have immediate practical applications. Although we were able to utilize most of the constructs, in those early algorithms to develop much more complicated and advanced algorithms, they didn't seem to have immediate practical applications. But on the other hand, the Shor's algorithm has an immediate application that would have a huge impact on the state of the art in cryptology. So that was the major reason why the quantum computers were developed. First, before going into Shor's algorithm, I would like to tell you a few simple facts about number theory, and in particular modular arithmetic. First of all, we know the fundamental theorem of arithmetic given capital N equals PQ. There are unique prime factors, P and Q. This is the fundamental theorem of arithmetic. We know also that the greatest common divisor of A and B is denoted as the function GCD of AB. And this is classically easy to compute. We just use in most high school curriculum, this algorithm is taught as the Euclid's algorithm, and it's easy classically to compute GCD of A and B. That's the greatest common divisor so that's the integer that divides, the largest integer that divides both A and B. If GCD of A and B equals 1, in other words, if the largest common divisor of two integers A and B equals 1, then we say that A and B are relatively prime. They are co-prime or they are relatively prime. As you must have seen in your earlier courses, modular arithmetic is A equals X mod N means that if remainder of A divided by N, capital N, is X, then we say A equals X modulo N. Right? Just by way of an example, let's consider the case when A equals 3 and capital N modulo 10. Just repeated exponentiation of 3A. 3 to the 1 equals 3 modulo 10. 3 to the 2 equals 9 modulo 10. 3 to the 3 equals 7 modulo 10. And then when we reach 3 to the 4 equals 1 modulo 10, this sequence becomes cyclic. In other words, 3 to the 5, again, it becomes 3. 3 to the 6, it becomes 9. 3 to the 7 becomes 7. And then we complete a second period when we reach 8. 3 to the 8 equals 1, modulo 10. So this is the case. If A and N, they are relatively prime, this is always the case. You always have this cyclic behavior. If you look at this cyclic behavior a little more carefully, we see that the last element of the sequence is always 1. Right? You start with 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, and when you complete a period, right, this last element is always of the sequence is always 1, and this indicates this exponent 3 to the 4 when 3 to the 4 equals 1 modulo 10. This indicates the period. The period of this sequence is 4 because starting from A to the 1, A to the 2, A to the 3, A to the 4, when we reach A to the 4, right, the exponent, when we take the exponentiation with 4, we reach the value 1. So that means the period of this sequence is 4. And if 3 to the I mod 10 for I equals 1 to up to infinity is a periodic sequence, right? We call this a cyclic function. So based on this definition, we define f sub a capital N. This is a function parameterized by small a and capital N. And we define these functions as a to the x modulo capital N. So, so this is a function of x. A and capital N are parameters of the function, and x is the input to the function. And we define this function as a to the x. And as we said, this sequence is always cyclic if a and capital N are relatively prime. In other words, if the GCD, the greatest common divisor of a and capital N, if this equals to 1, this one can prove that this sequence is always cyclic. As we'll see shortly, this prime factorization problem can be viewed as a period finding problem. In other words, if one can find the period given a sequence of numbers, if one can find the period in this sequence, then we practically also we have solved the prime factorization problem, because this problem can be mapped to the period finding problem. Shor's algorithm actually suggests a method, a way to compute this period R, that's the length of the cycle, efficiently using quantum circuits. So Shor's algorithm has a classical part and also a part that we implement using a quantum circuit. Let's go over the classical part first, and let's see where the quantum circuit part, enhances the efficiency of the algorithm. This classical part goes as follows. Given a number, capital N, this is a number I would like to factorize. We select an A, small a, such that the GCD of A and N equals 1. We can easily, we select this A randomly, but we can easily prove that this is the case using Euclid's algorithm. You can easily check this. So if the GCD of A and N is different from 1, then that means there is a common factor P. So we just divide capital N to P and to find the other Q. And output P and Q as the prime factors. But if GCD of A and N equals 1, then that means there's no common factor. We go to the second step. Now we compute the period R of this function, f sub a n of x, as we defined before, which was a to the x modulo n, such that a to the r equals 1 modulo n. Because as we have seen over here, and also it's possible to prove this theorem, the period of a sequence like this, of a to the x, is when we obtain a to the x equals 1. So that means that's the starting point of the period. And then when we reach another one, like when in this case a to the 8 equals 1 is 1, for instance, then it means we have reached the second period, another sequence. So we have completed another period of this sequence. So a to the r equals 1 modulo n means r is the period of this particular sequence. Classically, this is an exponentially complex problem. This is the part of the algorithm actually where Shor's quantum circuit is going to help us. Classically, this is a very hard problem. What you need to do is basically you go over a to the 1, a to the 2, a to the 3, and then up to the point where you reach a to the r equals 1. So for imagine if you have a large integer, large n, right? This would be an exponentially complex problem. And now, when you compute a to the r, when you find the r such that a to the r equals 1, if r is even and a to the r over 2 plus 1 is different from 0, we continue to step 3. As we go to step 1 to pick another a. So we want both conditions to hold. We want both the period to be n, a to the r equals 1, so the r, the period to be even, and also we want it to satisfy this condition, a to the r over 2 plus 1 equals 0. And we see shortly, why we require, these two conditions. So if the period r does not meet these conditions, we start all over and we select another a such that GCD of a and n equals 1. Okay. So now the third step is since r is the period, in other words, a to the r equals 1 modulo n, and this implies that a to the r minus 1 equals 0 modulo n, because if you just bring in, this one to the left-hand side, this equation becomes a to the r minus 1 equals 0 modulo n. By the definition of modular arithmetic, there exists an integer k such that a to the r minus 1 equals k times n, right? Because that's the definition, k times n equals 0. That was the definition, basically, of modular arithmetic. And this is the critical point here. You can factorize a to the r minus 1 as follows. This is just in the regular arithmetic, right? If you recall, x squared minus y squared can be factorized as x minus 1 times x plus y, x minus y times x plus y. So similarly, in modular arithmetic, you can do a similar factorization. A to the r minus 1 can be factorized as a to the r over 2 minus 1 times a to the r over 2 plus 1 equals kn. And n was pq, right? Kn equals kpq equals 0 by definition. So now the last and the fourth and the final step is looking at this equation. We see that p and q should divide one of a to the r over 2 minus 1 or a to the r over 2 plus 1, right? I mean, just by looking at this, these are the prime a to the r over 2 minus 1 and a to the r over 2 plus 1 are the prime factors, basically, because we said this equality, this equals kn equals kpq. So if you look at it, right, just by comparison, this part should be p and this part should be q. So then p is the GCD, greatest common divisor of a to the r over 2 minus 1 with n, and q is the GCD of a to the r over 2 plus 1 with n. So, and as we said, just by using the Euclid's algorithm efficiently, one can easily compute these GCDs and output P and Q. So we have actually, through this algorithm, reduced the problem of computing P and Q, the prime factors of a large n, large integer, to the problem of computing the period of the function a to the x. In other words, to compute x such that a to the r equals 1 modulo n, where r is the period of this sequence.